Our next topic is operations on functions. We're going to look at how we can add, subtract, multiply, and divide functions to get new functions. We're also going to look at a fifth operation called composition, which we use very often in order to sort of string together some functions. Let's look at an example of why we might want to look at operations like this. So let's say that the profit of a certain branch of a company is given by f of t equals, we'll do 3t plus 5, where t is years since the company was started, and f is measured in millions of dollars. So that gives us one branch. That gives us the profit of a single branch. The profit of the second branch is given by g of t equals 1/2 t squared plus 1, measured the same way. What is the total profit of the company as a function of t? So this problem is asking us for a function that will take t, a number of years since this company began, as an input and give as an output the total profit of the company. Now, before we actually write down a formula for this, let's look at things for particular situations. So, for example, let's consider t equals 4. So let's consider what the profit of the company is 4 years after the company starts. Well, what we need to do to figure this out is to figure out the profit that each of the branches had 4 years after the company started, and then combine those together. So if t is equal to 4, then we have that f of 4 is equal to 3 times 4 plus 5 is 17. So the first branch had a profit of $17 million 4 years after the company began. And g of 4 is 1/2 times 4 squared plus 1. Now 4 squared is 16, 1/2 of 16 is 8, and 8 plus 1 is 9. So g of 4 is 9. So this tells us that the second branch had a profit of $9 million in year 4. So that means that the total profit is 17 plus 9, which is 26, when t equals 4. Now, of course, there was nothing special about 4 here. We would go through the same process if t were any number. We'd evaluate what the profit is at the first branch and what the profit is at the second branch, and then we would just add those two together. So in year t, the profit will be f of t plus g of t. It'll simply be the sum of the profits of the two branches. Now, we can also write this a different way. We know that for any value of t, f of t is 3t plus 5, and g of t is 1/2 t squared plus 1. So instead of writing f of t plus g of t, we could write 3t plus 5 plus 1/2 t squared plus 1. And, of course, we can simplify this a little bit But this is a formula that defines a perfectly good function. And this function that's defined by this formula is what we are going to define the function that we get when we add f and g together. So we're defining operations here on functions, where we're going to add two functions together and get a new function out of it. So let's look at the definition. So let's let f and g be functions. The sum of f and g is the function which we write as f plus g. Now, we think of the expression f plus g as a single expression. This is a single function. Now, it's built up out of f and g, which is why they show up in the notation, but this is a function. And in order to define a function, I need to tell you what happens when you plug in some input. So when I take some input x to the function f plus g, the output of that function will be the number that we get, or the value that we get, when we evaluate the two functions f and g at x and add them together. And once we see this pattern, the exact same pattern is going to apply for the other three basic arithmetic operations. The difference of f and g is the function f minus g, where f minus g, evaluated at x, is defined to be f of x minus g of x. The product of f and g is fg, or sometimes f times g. Of course, we often don't write the multiplication symbol in between two symbols that we're multiplying, often. But it's going to turn out that in the case of functions, it's often going to be better for us to be explicit about it and actually write the dot in between. And we'll see why when we get to our fifth operation of composition. The product of f and g is fg, or f times g, where we have that f times g evaluated at x is f of x times g of x. And this product here is just a product of two numbers. And finally, the quotient of f and g is f over g, where f over g of x, or sometimes we write it this way, is f of x over g of x, and this is only if g of x is not equal to 0. Okay, so let's look at a few examples. Let's let f of x be x squared plus 1 and g of x be 3x minus 2. Let's find f plus g, f minus g, f times g, and f divided by g, and their domains. Let's start with just finding the four functions that we have here. So part 1, if we want f plus g, the way that we're going to describe the function f plus g is to describe what happens to it when you plug in a number x. Well, f plus g of x, by definition, is f of x plus g of x. Now, f of x, we know, is x squared plus 1, and g of x is 3x minus 2. So we can combine these together and get that this is x squared plus 3x minus 1. So that's the function f plus g of x. I'm going to leave space down below here for when we talk about the domain. F minus g of x goes similarly. That's just f of x minus g of x, which is x squared plus 1 minus 3x minus 2. Make sure that when you are doing this subtraction, you put a parenthesis around the formula for the second function so that the negative distributes properly. So when we do distribute this negative, we're going to have x squared, and then we'll have minus 3x, and then we have plus 1, and then minus a negative 2. So that'll be minus a negative 2 will become plus 2, so that'll give us plus 3. For part 3, we have f times g of x is equal to f of x times g of x. And here you want to make sure to put parentheses around both function formulas because you need to make sure to expand them properly. Now when you do expand this out and FOIL all this out, we wind up with 3x cubed minus 2x squared plus 3x minus 2. And so that gives the formula for f times g. Now, the next one is f over g of x, and that is defined to be just f of x over g of x, following the same pattern. And so that gives us x squared plus 1 over 3x minus 2, and there's really not a whole lot else we can do with that. So that's how we get the formulas for the 4 basic combinations of functions: the sum, difference, product, and quotient. Now let's talk about their domains. Remember that the domain of a function is the set of all numbers that you can plug into a function and get something meaningful out of it. Now, for the first 3 functions, the domain is going to be all real numbers. Notice that the domains of the original functions are both all real numbers. You can plug any numbers in there. And because we can add, subtract, or multiply any numbers together, forming the sum, difference, or product of these 2 functions will never cause a problem with the domain. So for each of these, the domain is all real numbers, negative infinity to infinity. However, for the last quotient here, our domain is not going to be all real numbers because we have a function in the denominator, and we need to make sure that that function does not equal 0. So we cannot let g of x equal 0. If we did, then we'd have a 0 in a denominator, and that wouldn't be defined. So we find where g of x equals 0, which means where 3x minus 2 equals 0. And if we solve that for x, we find that that happens exactly when x is equal to 2/3. So that's the number that we can't plug into this function. If we try plugging 2/3 into this function, then we will get a 0 in the denominator, and that will give us an undefined function. So this function's domain is all real numbers except 2/3. So the domain is negative infinity to 2/3, not including 2/3, union the interval from 2/3 to infinity. And that's the care that we need to take here. Let's look at a more systematic approach to the domain. All right, so here's the fact that we use. the domains of the functions f plus g, f minus g, and f times g are the set of all points, of all numbers, I should say, in the domains of both f and g. Another way of saying this is that this is the intersection of the domains of f and g. So in order for the functions f plus g, f minus g, or f times g to be defined, you do need both of the original functions to be defined, but that's all you need. The domain of f over g is the set of all x's such that x is in the domain of f and g, and g of x is not equal to 0. So the domain of the quotient is more restricted than the domains of the originals, or of the other three, rather. So let's take an example. Let's let f of x be the square root of x plus 2, and g of x be 1 over x minus 3. In order to figure out the domains of f plus g, f minus g, f times g, and f over g. Oh, pardon me, I had a typo here. We want g of x to be x over x minus 3. Let's look at the domains of each of these. So to find the domain of f, we look at our function f and we see that we've got a square root. And we remember that in a square root, the inside needs to be greater than or equal to 0. That's the condition that defines the domain. So we'll take x plus 2 and set it equal to 0. And when we solve for x, we get that x has to be greater than or equal to negative 2. So this is the condition that defines when a number x is in the domain of f. Now, how about the domain of g? In order for g to be defined, we need to have that the denominator of our fraction is not 0. So we need x minus 3 to not be equal to 0. Or in other words, we need x to not be equal to 3. So these are the two conditions on f and g that define their domains. Let's combine that information with the definitions of the combinations of functions like we have here in order to figure out the domains of f plus g, f minus g, and f times g, and f over g. So we got this information here. Now we can find the domains of f plus g, f minus g, and f times g all at the same time because they all have exactly the same domain. So, So the domain of f plus g, f minus g, and f times g is the intersection of the domains of f and g, meaning it's the set of all points that are in the domain of f and in the domain of g. One way that we can work this out a lot of times is using the number line. And we can illustrate the domain of f and the domain of g on a number line and see where they have overlap. Where they have overlap is precisely where the domain of f plus g, f minus g, and f times g are going to b. So we can see that the domain of f is the set of all numbers from -2 onwards, including -2. Whereas the domain of G is the set of all numbers other than 3. So we can illustrate that domain this way. Now, the domain of f plus g, f minus g, and f times g will be the set of all points that lie in the overlap between them, all the points that satisfy both of these conditions at the same time, that are greater than or equal to -2 and not equal to 3. So we'll do that in green here. So we're going to include all the numbers that are greater than 2 except 3, and including all the numbers greater than 3. So that's the domain of f plus g. So our answer here for the So for the domain of f plus g, f minus g, f times g, that's going to be the union of intervals from -2 to 3, not including 3, and then from 3 to infinity. So that's the green line that we have on the diagram. So that's the domain of f plus g, f minus g, and f times g. So that's all great. Now let's consider, what about f divided by g? Now, we don't actually want to get rid of the work that we've done. The work that we've done is good because the domain of f over g is going to be contained in the domains of f plus g, f minus g, and so forth and so on. But we might lose more things. So to find the domain of f over g, we want to set g of x equal to 0 and then remove any solutions. So let's go ahead and do that. We've got if g of x is equal to 0, that's the same thing as saying x over x minus 3 equals 0. And here we're going to solve for x. So we can multiply both sides by x minus 3 to get rid of that denominator. The x minus 3's will cancel on the left, and so we'll get x equals 0. So that tells us that g of x is 0 if and only if x is 0. So that means that 0 is not in the domain of f over g. So we can come back up to our diagram here, put in a new point here, and draw in a new open circle. So the domain of f divided by g now will include all the numbers greater than or equal to -2, but not including 0 and not including 3. So that means that the domain of f over g is the interval from -2 to 0, unioned with the interval from 0 to 3, unioned with the interval from 3 to infinity. So this is the way that we can find the domains of the sum, difference, product, or quotient of functions. Now, it's very important that we go through this process carefully, because if we just look at the formula that we get when we evaluate f plus g or f minus g or f divided by g or f times g, we won't necessarily detect some of the points that aren't in the domain. Let's take a little warning example for this. Let's let f of x be 1 over x and g of x be 3x minus 1 over x. Let's find the domain of f plus g. So let's do it the right way, and then we'll see what can go wrong if we don't do it this way. So doing it the right way, we want to look at the domain of f and domain of g separately. Now f, we see, has an x in a denominator, so that tells us that x cannot be 0. And that's the condition for the domain of f. The domain of g is actually the same because g also has an x in a denominator. So the domain of f is all real numbers except 0. The domain of g is all real numbers except 0. And so the domain of f plus g is the set of all numbers other than 0. Or we could write it in interval notation as the interval from negative infinity to 0 union the interval from 0 to infinity. However, if we went about this the wrong way, if we started by getting an expression for the function f plus g of x, that would be 1 over x plus 3x minus 1 over x, and we could notice, oh, those are two fractions, they have the same denominator, we can combine them. We can get 1 plus 3x minus 1 over x, which gives us 3x over x, and now we'd be tempted to simplify this to get down to 3. Now, what is the domain of the constant function 3? Well, it's all real numbers because there's nothing that can go wrong. There are no fractions or square roots that can cause us issues here. And so if we went ahead and simplified our sum here as far as possible, we get an expression which would suggest that the domain of this function is all real numbers, but in fact it's not. Even though this function's expression simplifies down to 3, the domain of this function is still undefined. In fact, the proper way of writing down the simplification for this function would be to say that the function f plus g of x is equal to 3 if x is not equal to 0 and undefined if x equals 0. And this is just a pretty simple example. More complicated examples can definitely come up. So you never want to figure out the domain of a combination of functions based on the simplified form of it. The simplified form of the function is not good enough. You need to do it by working with the domains of the original functions that went into the combination. All right. So the next thing that we want to do is to recognize how to break up functions. We've looked at how we can take a couple of functions and combine them together, take two functions and find their sum, difference, product, or quotient. Sometimes, though, what we need to do is to look at a function and say, I can write this function as a combination of two simpler functions. So we could look at something like the following. Let's write the function h of x equals 3x squared minus 2 over 4x plus 1 as a quotient f over g for functions f and g. So this problem is asking us to find two functions f and g such that h equals f over g. So there are always many different possible ways of doing this. However, there are usually some obvious ones. So what we want to do is we want to take the expression for h, 3x squared minus 2 over 4x plus 1, and try to recognize it in the form that we're being asked to describe it, as a quotient of things. So we want to be able to write this as a quotient of some f of x function over some g of x function. And as we see here, the answer is kind of shouting at us. It's not too hard to come up with a way for this to happen. So we could do this in the following way. We can say, well, let's go ahead and let f of x be 3x squared minus 2. And let's let g of x be 4x plus 1. And that works. And that's the most useful form here, most useful answer here. Typically, we are only going to be interested in breaking up a function like this in its most obvious ways. Those are going to be the most useful ways, usually. So we can write h of x as this quotient of functions, and that can be useful in many cases. Sometimes you will have problems or techniques that you can use that are better applied to a quotient of functions than to just a single function itself. Also, the individual functions that we deal with here, f and g, are simpler than the original function h. So for instance, if we wanted to know the domain of the function h, we can use our rules that we just talked about to write down h as a quotient of these functions, and then use the rules that we have back there. Now, as I said, there's not always a unique way of doing this. In this case, one way of doing it really sort of leaps out at us. But let's look at another example where there are lots of different ways of breaking up the function, and it's not obvious which way that we should do it. So let's find f and g such that h equals f times g, where h of x is equal to 3 times x to the 7th. Now here there are a lot of different ways that we could write down h as a product of two functions, f and g. So let's look at just a few of them. We could have h of x being 3 times x to the 7th. This would give us this might give us the situation where f of x equals 3 and g of x equals x to the 7th. That's a perfectly good way of doing it. But we could also break it up a number of other ways. We could write it as 3x times x to the 6th, in which case f of x could equal 3x, and g of x could equal x to the 6th. This is also a perfectly good way of writing down the function h as a product of two functions f and g. There are lots of other ways that we can do it as well. Of course, 3x to the 4th times x cubed, so we could have f of x be 3x to the 4th, g of x be x cubed. We could even rearrange the order of these things a little bit. We could have x to the 5th times 3x squared, so that f of x is x to the 5th, g of x is 3x squared. We could even do something where we split up the constant term and write something like h of x is 9x cubed, and then 1/3 x to the 4th. So we could take f of x is 9x cubed, g of x is 1/3 x to the 4th. These are all perfectly good answers to this problem, and all of these would be perfectly acceptable if this was the only question that was being asked. Which one of these is most useful to us depends very much on the context of the problem that we're working in. A lot of times, it's useful to split functions up into just the coefficient piece and then a piece that's just some power of a variable. Other times, you want to split up a function into two functions where the two functions that you get are, say, of much lower degree or as low degree as possible. So instead of dealing with an x to the 7th, we've got an x to the 4th and an x cubed to deal with. That can work also. There are lots and lots of different ways that we could split up a function as a sum, difference, product, or even quotient of two others. Sometimes it's obvious, as in the first example that we did. Usually there's an obvious way to write down a function as a quotient of two other functions. But for a product here, it's highly non-obvious which way is best to do it, and it depends very much on the context of the problem. And it's even worse for sums and differences. There are just so many ways of writing down a function as a sum or difference of two other ones. So this is something that we look at. It's usually more important to recognize that a function can be written down as a product of things and use that when necessary than to always be thinking about it. Because most of the time you don't need to do this. Most of the time you can just work with the function h as 3x to the 7th and just leave it there. But sometimes you do want to split it up. All right, now let's talk about composite, or the composition of functions. This is new, and this is an operation that doesn't come from any sort of operation on numbers. This really is something that's very special about functions. So what I want to think of is I want to think of our functions as being sort of machines that take an input and give an output. So we could think of a given function f here, or actually I want to call this function g. And this function g can take a number as an input and give another number as an output. And I could have another function f over here, which can take an input and give an output. So if we get an x in here, we get an f of x out of here. And we can even think of these functions as being very much like mechanical processes, where you've got one machine which flattens the sheet of metal and another machine which etches a design into it. So what we can ask is, well, what happens if we try to hook up the machines? What happens if we take the output of this function and run it into this one? Well, then we can sort of combine the two machines together into one bigger machine and see what we get. Now notice that when we do this, the input to the f function here is no longer x, but it's the output of the original one. It's g of x. So now, with the connection that we've done, we're now plugging g of x into this function. And what we get out is going to be not f of x, but f of g of x. So what we've done going through this process is we've taken an input x, and then we've applied g to it, and we've applied the function g, and we've gotten g of x, an output from g, which is some number. But then we've taken that and put it in the other function f, and gotten an output out of this. And so the outputs of the function g become the inputs to the function f, and we get a new function that takes an input x and gives an output that we write as f of g of x. This is composition of functions. It's stringing functions together, plugging an input in and applying several functions in sequence to it and seeing what you get out of the end. So let's look at the definition. The composition of f and g, first of all, is denoted. We need a new symbol for this because this is a new type of operation that we haven't used before. And the symbol that we're going to use is an open circle. So not the dot that we use for multiplication, but an open circle. And this is a function, and it's defined by exactly the formula that we had up above. If I look at the composition f of g and I apply x to it, or I apply it to x rather, that's going to give me f of g of x. This notation is sometimes known as fog notation, as in the word fog, because it sort of looks that way. And it's defined like this. Whenever you're going and evaluating a composition of functions, you are basically always going to use this form of it because that's the definition of the composition of two functions. So let's do some examples with this. So let's let f of x be x squared plus 1 and g of x be 2x minus 3. Let's find f composed with g of 2, g composed with f of 2, f composed with f of 1, and g composed with g of 0. So all of these evaluations are going to go basically the same way. If I want to know f composed with g of 2, the first one here, I'm going to use the definition. The function f composed with g of 2 precisely takes the input 2, first applies g to it, gets a number out of that, and then figures out what f of that number is. So we have f of g of 2. Now at this point, we can actually go over to the side here to figure out what g of 2 is. So using our definition, g of 2 is 2 times 2 minus 3, which is 4 minus 3, which is 1. So that means that g of 2 is 1. And so f of g of 2 is f of 1. We're working from the inside out, and this is a strategy that we're going to use very often when dealing with composition of functions. Now, f of 1, we can look back up at our definition for f. And at this point, we can sort of forget where that 1 came from. We just need to figure out what do we get when we plug 1 into the function f. And we'll get 1 squared plus 1, which is 2. So we find that f composed with g of 2 is 2. All right, let's do the next one. What if we have g composed with f of 2? Now, it's important to keep track of the order here. The order that you get when you write down the composition in the way that we just did is the same as the order that you write down the notation in the fog notation, or in this case, it's g composed with f, so it's sort of Goff notation. So g composed with f of 2, we could figure out what f of 2 is over here. F of 2 is 2 squared plus 1. 2 squared is 4, plus 1 is 5, which means that g of f of 2 is equal to g of 5. Now we can use the definition for g. G of 5 will be 2 times 5 minus 3. 2 times 5 is 10, So 2 times 5 minus 3 is 7. So that means that g composed with f of 2 equals 7. Now, before we go on, I want to point out something very important. The first example we did composed f composed with g and evaluated that function at 2. And when the input to that function was 2, the output was 2. Our second function had g composed with f of 2, which gives 7. And so when this function has an input of 2, the output is 7. In particular, note that these are different. And this illustrates the following fact that often, in fact, usually, f composed with g is not the same as g composed with f. So in other words, composition of functions is not commutative. The order very, very much matters. So be very careful when you are working with composition of functions that you're getting the order correct and using the definition carefully. Remember that the order that the functions show up here in the Fogg notation is the same as the order the functions show up in the broken up notation, like here. All right, let's do the next. We can compose a function with itself. That's perfectly fine. That's like taking the output to a machine and wrapping it back on it and running it through the same machine one more time. So we can write this as f of 1. And rather than doing things off to the side, we actually can do everything all together. So I'm going to leave the f on the outside alone. Now the f of 1 on the inside, I'm just going to go ahead and plug that into the function f. So f of 1 is the same as 1 squared plus 1, which gives f of 2. And we actually already know what f of 2 is. We did that before. F of 2 is 5. So that means that when we compose f with f and evaluate it at 1, we get 5. Similarly, when we compose g with g and get 0, that's g of 0. Now g of 0 we can get by plugging 0 into the function g. So we'll get g of -3. And then when we look at g of -3, that'll be 2 times -3 minus 3. That'll be -6 minus 3 is -9. And so this is how we can evaluate a composition of functions at specific numbers. So now let's talk about how we can write down a formula for the composition of functions. Let's use these same functions again. But now let's write down their compositions as functions using formulas involving x. So let's find f composed with g of x, g composed with f of x, f composed with f of x, and g composed with g of x. So here we're going to be getting formulas for these. So to get f composed with g of x, we're going to do things in very similar ways to how we did them before. The difference here comes at this step. Rather than being able to replace the inside expression here with just a single number, we replace it with an expression. If I want f of g of x, remember that g of x means the output of the g function when the input is x. We know from up above that when the input to the g function is x, the output is 2x minus 3. And therefore, instead of writing g of x here, we can write 2x minus 3. That is what g of x is. So we get f of 2x minus 3, and now we can use f. Now here we have to be a little more careful because now the expression that we're plugging into f is 2x minus 3. That's taking the place of the x in the original function f, which means that we're going to replace each x in the description of f with this new input expression of 2x minus 3. So this is going to give us, instead of x squared plus 1, we will get 2x minus 3 squared plus 1. Now we can go ahead and expand this out a little bit. If we FOIL this out, we get 4x squared minus 12x plus 9 plus 1. So, in conclusion, for this first part, we have that f composed with g of x is equal to 4x squared minus 12x plus 10. This is telling you that if you take the an input x and apply the function g to it, and then take that output and apply the function f to that, what you will get is 4x squared minus 12x plus 10. You'll notice that the composition of functions here is more complex than either of the original functions. This is usually the case. Usually a composition of functions will give you a more complicated function than either of the ones that you started with. Now let's go the other way. Let's look at g composed with f of x, and we're going to use exactly the same strategy. G composed with f of x is the same as g of f of x. Now f of x is x squared plus 1. So now if we plug x squared plus 1 into g, we're going to be replacing the variable x with x squared plus 1. So we get 2 times x squared plus 1 minus 3 gives us 2x squared plus 2 minus 3 will give us 2x squared minus 1. So you'll notice, again, as we pointed out last time, that these two functions are very different from one another. They almost don't look related at all. It'd be very difficult to recognize that they are built out of the same functions, just composed in the opposite order. All right, let's see what happens if I take f and compose it with itself. F composed with f of x. Really, nothing's too different when you're applying a composition of a function with itself. We are going to get f of x. We know f of x is x squared plus 1. And now we're going to be plugging the expression x squared plus 1 into the function f in place of the x. So this is going to give us x squared plus 1 squared plus 1. So from here we can expand this out. We'll get x to the 4th plus 2x squared, and when we expand all this out, we wind up getting plus 2. And then finally, we can take g composed with g of x. That's going to be g of x, which will be g of 2x minus 3, which gives us 2 times 2x minus 3 minus 3. So we've taken the expression for g of x and plugged it back into g of x in place of x. And when that's all said and done, we're left with 4x minus 9. So this is the general process for finding the composition of functions. It's as expressions. They pretty much go the same way no matter what you're working with. Now, the thing that is a little bit more complicated about compositions of functions as compared to sums, differences, products, and even quotients is determining the domain. Because we're stringing functions together, we've got a slightly more complicated way of figuring out what the domain of the composition is. So let's look at the domain of the composition f composed with g. And let's keep in mind our picture from before. Here's the process. We are going to take an x and plug it into the function g, get g of x out of it. We're going to take that and plug it into f, and out of that we'll get f of g of x. Now we want to ask what has to be true at each one of these steps for us to actually get something out the other side. We want to be able to get all the way from x on the left to f of g of x on the right, and we want to know what has to be true about the function x for that to happen. Well, let's look at both stages. So the first step, going from x to g of x, for this to work, x must be in the domain of g. If x were not in the domain of g, then we wouldn't be able to get any output to it. If x weren't in the domain of g, then trying to put x into the g function, the g machine, would cause things to break. Nothing would come out the other side. So in order for that first step to happen, x must belong to the domain of g to begin with. Next step, we are taking the value g of x and plugging it into the function f. Well, in order for us to get anything out of that, the thing that we plug into f must be part of the domain of f. So for this to work, g of x must be in the domain of f. Must be in the domain of f. Now, if both of those are true, then we're good. Then we actually get an output. We'll be able to get an f of g of x. And so this leads us to how we determine the domain of a composition. The domain of the composition f composed with g is the set of all x in the domain of g such that g of x is in the domain of f. Notice in particular that x does not have to be in the domain of f. In fact, very often it won't be. But g of x has to be in the domain of f in order for this to work. So let's look at some examples and see how we can figure out the domain of the composition. Before we start, I should warn you that just like with adding, subtracting, multiplying, and dividing, it's not good enough just to figure out the formula for the composition and look at the domain of that. Very often, the composition's formula will appear to be defined at places that aren't actually in the domain of the composition because of some simplification that's happened. So it's important to keep that in mind. All right, so let's see some examples. Let's find the domain of f composed with g where f of x is equal to x cubed minus x squared, and g of x is equal to 4 plus x over x. Now, one thing that is nice about just the question of finding the domain is that often you don't have to figure out the formula for f composed with g. We will do this after we work out the domain just for an additional bit of practice, But notice that if the problem is only asking for the domain, you don't have to work out what the what the formula for f composed with g is. Okay, so let's look at this. To find the domain of a composition, we've got a couple of steps. So step one, we are going to need to find the domains of f and g. Now, even though the domain of f might not be the domain of f composed with g, it's still used in figuring it out, so we will need to figure out what both of those domains are. So let's see here. The domain of f, notice that this function f is is defined using a polynomial. It's got values of x that are being raised to powers and subtracted. Nothing there can go wrong. There are no roots, there are no fractions, nothing can go wrong here. And so the domain of f is actually all real numbers. From negative infinity to infinity. This is actually quite nice for us because it means that as long as the numbers we look at are in the domain of G, they'll be in the domain of the composition. So let's look at the domain of G. For the domain of G, we can see that the formula for G has a fraction and has a variable expression in the denominator. And we need to make sure that that is not equal to 0, so the domain of G is x is not equal to 0. So the domain of G is going to be part of what we use to, or rather the domain of the composition has to be also part of the domain of G. The domain of the composition might be more restricted than it, but it will definitely have this condition for x not being equal to 0. So then step 2, find all x's that make g of x in the domain of f. So in this problem, this step is trivial, and that's because the domain of f is all real numbers. So in this case, all numbers work, because the domain of f is all real numbers. Therefore, the domain of the composition is going to be the set of all numbers in the domain of G, full stop. Because normally it would be all numbers in the domain of G such that g of x is in the domain of f, but g of x is always in the domain of f if it's defined, because the domain of f is all real numbers. So for our problem, our answer is all real numbers other than 0, or in other words, the interval from negative infinity to 0, union with the interval from 0 to infinity. Now, as I said, for practice, let's go ahead and work out what f of g is. So let's look at f of g of x. This is going to be f of g of x, which will give us f of 4 plus x over x, which is 4 plus x over x cubed minus 4 plus x over x squared. So notice that whatever we plug into f here goes into all instances of x that appear in the formula for f. Now that can be expanded further and simplified. That's not super necessary here, so I'm going to go ahead and leave it for a moment. But it's decent exercise if you want to stretch your muscles with simplifying expressions like this. Let's look at another example. Let's find the domain of f composed with g, where f of x is equal to the square root of 4 plus x, and g of x is equal to x plus 2 over x minus 4. All right, this is going to be a little bit more complicated here. So let's look at the domain of f. Now, f has a square root in it, which means that the inside part of the function inside part of the square root has to be greater than or equal to 0. That's the same thing as saying that x has to be greater than or equal to -4, and we want to put our domain in the simplest possible form. So then the domain of g is that x has to not be equal to 4, because that's the number that will make the bottom of this fraction equal to 0. So that was step 1. So now we want to find the x's that make g of x be in the domain of f, i.e., we want to solve the inequality g of x is greater than or equal to -4. We're using the domain of f, and we want to we see that the domain of f says that the input to f has to be greater than or equal to -4. And since in the composition the input to f is g of x, we need to make sure that g of x is greater than or equal to -4. And now here's where things can get a little bit complicated, and where they are here. So that gives us that x plus 2 over x minus 4 is greater than or equal to -4. Now here's where we need to go back and use some of our techniques for solving inequalities, and you might have to review a little bit of that. That's okay. Remember, for inequalities, for rational inequalities like this, we will typically want to get all of our numbers on one side and get just a 0 on the other side. So we get x plus 2 over x minus 4 plus 4 is greater than or equal to 0. Now, x plus 2 over x minus 4 plus 4 we need to combine into a single fraction, so we'll multiply this 4 by x minus 4 in the numerator and denominator, getting us a common denominator between these two. And if we add these together, we'll get x plus 2 plus, distributing this 4 through, we'll get 4x minus 16 all over x minus 4 is greater than or equal to 0. And you can see that this process can take a little bit. So we get 5x and then plus 2 minus 16 is minus 14 over x minus 4 is greater than or equal to 0. Now remember, at this point, we want to take our number line and split it up. And we're going to split it up at any point that makes the numerator or denominator equal to 0. So the denominator is equal to 0 when x is equal to 4. Let's see. Pardon me. So 4 is where the denominator would be equal to 0. And the numerator is equal to 0 when x is equal to 14/5, which is a little less than 3. And now remember, what we want to do is we want to plug a representative from each one of these intervals into the inequality here to see whether we get a true statement or not. So from the first interval we can pick 0, From the second interval, we can pick 3, because it turns out that 3 is just a little bit more than 14 over 5. And from the right-hand side over here, we could pick 5. So if we plug in 0, then we get 5 times 0 minus 14 over 0 minus 4 is greater than or equal to 0. And that's going to give us a negative 14 over negative 4 is greater than or equal to 0, which is true, because a negative divided by a negative is a positive, and that'll be greater than or equal to 0. Now if we plug in 3, we get 5 times 3 minus 14 over 3 minus 4 is greater than or equal to 0, which tells us that 1 over negative 1 is greater than or equal to 0. That's false, so we get rid of that part. And then we have, if we plug in 5, we get 5 times 5 minus 14 over 5 minus 4 is greater than or equal to 0, is equivalent to, let's see, 5 times 5 is 25, minus 14 is 11, then 5 minus 4 is 1, greater than or equal to 0. That's true. And so what we see is that our solution to this inequality will include the intervals up to 14/5 and to the right of 4. Now we do need to make sure that we keep track of for each one of these endpoints whether they're included or not. So the 14/5, so first of all, notice that we're looking for a greater than or equal to. So the endpoints might be included. If we were looking for a greater than here, then the endpoints would not be included ever. But in this case, we're looking for a greater than or equal to. This 14/5 came from the numerator. So the 14/5 was the x value that makes the numerator equal to 0. And the numerator being 0 is fine. So we're going to include a solid dot there, or equivalently a square bracket. However, the x equals 4 portion of that came from the denominator, so that's not going to be included. All right, so what does all this mean? We were trying to find the conditions on x that would make g of x be greater than or equal to negative 4, because that's what makes g of x to be in the domain of f. So we have that these intervals will make g of x be in the domain of f, and so that's the second part of the condition that we need. So let me give myself some more space here. So this is what we had before, and what we found is that g of x is in the domain of f if x is in the following set: the interval from negative infinity to 14/5 union the interval from 4 to infinity. Now we need two things to be true for in order to find the domain of f. We need to, in order for x to be in the domain of f, we need this condition that we have here, and we need this condition. We need two things. We need x to be in the domain of g, and we need g of x to be in the domain of f. And as long as both of those things are true, then we have our domain. So notice that if x is in this this union of intervals down here, then we already have that x is not equal to 4. So in fact, we have that the domain of f composed with g is this interval right here, negative infinity to 14/5 union the open interval from 4 to infinity. Now, as this example shows, finding the domain can sometimes be a bit of a process and can often use some of the algebraic techniques that we've looked at previous times. All right, the next thing we want to look at is how to recognize that a function is a composition of functions and to write it as a composition of functions. Just like with the previous examples, this is often very important. And so let's take a look at it. So let's look at the example. Let's write h of x equals 1 over x minus 3 as f composed with g. Or in other words, let's find f and g to make this happen. So what we want to do on expressions like this is basically we want to try and identify an outside function and an inside function. A good way of thinking about compositions is that the g function, the expressions for the g function, get plugged into the f function, and so the g function is sort of sitting inside the f function. That's a common way to think about it. So the way that I would do, the way that I would look at this expression and try to split it up is I'd look for some function, some expression that's not the whole thing, not the whole expression, but sort of sits inside the function. And in this case, what I might choose is this x minus 3. I might say, all right, well, let's note this x minus 3 here, and maybe I'll try making this g of x. So if I made that g of x, then this expression would turn into 1 over g of x. And now if I want this to be f of g of x, then I can figure out what f should be by taking this expression and kind of going backwards. Let's replace g of x with just x. If we replace this g of x with just x, we get 1 over x, and that's what we can let our function f of x equal. So in this problem, we can let f of x equal 1 over x and g of x equal x minus 3, and that gives us what we need. Now, if we do take f composed with g of x, that's going to be f of g of x, which is x minus 3. And because f of x is 1 over x, this will give us 1 over x minus 3, which is exactly what we started with. You can always check your work going through this process simply by taking the composition of your proposed f and g and making sure that it works out properly. Let's look at another example. Let's write h of x equals 3x plus 2 squared minus 1 as f composed with g. So once again, we'll go through the same process. We could write 3x plus 2 minus 1, and I want to try to identify some expression in here which is an inside function. And there are actually lots of possibilities here. So let's look at a few of them. We could take the 3x part of the function to be the inside part. We could make the whole 3x plus 2 part to be the inside part. Or we could go even further, make it 3x plus 2 squared being the inside part. And any of these could work. And if we take just 3x to be the inside part, the part that we replace with g of x, then that means that f would be the function x plus 2 squared minus 1 in this first case. In the second case, we would replace our whole inside function with x. Make that x squared plus 1, or minus 1. And if we replaced all of 3x plus 2 squared with x, we would just get x minus 1. So here are some possibilities based on the examples we just did. We could take f of x be x plus 2 squared minus 1, and g of x equals 3x. We could take f of x to be 3x plus 2. I'm sorry, I got that backwards. F of x to be x squared minus 1, and g of x to be 3x plus 2. And we could take f of x to just be x minus 1, and then g of x to be 3x plus 2 squared. All of those are possible decompositions of h into f and g such that f composed with g is h. Which one of them works best depends very much on the context of the problem. If any of you do go on to calculus, this process of writing a function as a composition of two other ones is actually essential. It's very, very important and a very, very powerful technique that you'll use when you'll get there. All right, last thing for today, I want to look at a simple application problem where we can use composition of functions to understand what's going on. So let's say that the temperature of an object is increasing at a rate of 5 degrees Fahrenheit per hour, and its temperature is given by f of t is equal to 100 plus 5t, where t is measured in hours since the experiment began. However, perhaps you don't want things in terms of Fahrenheit, you want things in terms of Celsius. Now, the temperature in Celsius is a function, I should say, of the temperature in Fahrenheit, given by the Celsius temperature of a the Celsius measure of a temperature with x degrees Fahrenheit is given as 5/9 times x minus 32. If you take your temperature Fahrenheit, subtract 32 from it, multiply it by 5/9, then you'll get your temperature Celsius. Then the question is, what is the temperature Celsius as a function of time? So here, if I want to know what the temperature is of the object at a particular moment, I have a process I can go through, and the process that I go through will illustrate to me what sort of composition I should use here. So let's imagine that I just knew the temperature at a certain point. or rather, I knew the time. I knew the time. And I wanted to figure out what the temperature Celsius was. Well, I would go through two steps. I would take the temperature, or the time rather, and find the temperature as a temperature Fahrenheit. So that's what the function f does. It takes a time, gives me a temperature. But that temperature is in Fahrenheit, and so then I would apply the function C, which would give me the Celsius degree measure of that Fahrenheit temperature. But notice that this is exactly the function C composed with f. Whenever you're going through a process where you apply one function or one process and then another process in sequence, you're really doing a composition of functions, and we can combine things together that way. So, to answer our question, we can look at the composition C composed with f of t, and by definition, this is C of f of t. We know that f of t is 100 plus 5t, and now we can plug that into the function c. So that's going to give us 5/9 times 100 plus 5t minus 32. So this gives us a function, 5/9 times, we can simplify it by combining the two constant terms here, 5/9 times 68 plus 5t, and that gives us the temperature of the object in Celsius based on the number of hours since the experiment began.